Okay, let's get started now. From today we will start a new part of a new module. Where we will basically see the applications of machine learning and deep learning techniques in various domains of Earth system science. So the first domain with which we will start is remote sensing or Earth observations. So as we know that there is currently a huge network of various kinds of satellites which are encircling the Earth and which are capturing images at a high spatial and temporal resolution. So from every satellite image, like we can actually get the view of like a large of a particular region at quite high spatial resolutions nowadays, and at regular intervals of times also. I mean, like there are even like hourly views are available. So the question is, so with this vast amount of Earth observations available, what can we do with it? So first of all, the things that, I mean, the images that are captured by the satellite, from those images we can directly process them to infer certain things, or like about the like that is we can treat those images as normal images. That is the kind of images that we have access to in our daily lives, and try to make sense of them or try to get information from them. Alternatively, we can actually use those images in that is not just in the normal visible range image, but the visible spectrum image, but also say hyperspectral images and so on. And typically these imagery are used to infer or estimate the values of various atmospheric variables which are otherwise would have been otherwise difficult to estimate. Say for example, the cloud cover or humidity at different heights and so on. So these are not directly measured by the satellites, but from the imagery that are captured by the satellites, it is possible to use or it's possible to predict the values of these quantities with the help of machine learning. That is, we can try to find out some relations, like if the satellite imagery is like this, looks like this, then then it probably means that the moisture content of the air at such depth is so much, and things like that. So these kind, so that is, so like these are, it's like these techniques are known as proxy techniques, where we are not measuring the quantity of interest directly, but rather we are capturing the satellite imagery, and from the satellite imagery we are trying to estimate some, or we are trying to build some kind of a relation between the satellite imagery and the quantities of our interest. And those relations are typically developed or modeled with the help of machine learning approaches. So those things we will see in the subsequent lectures. Today, let us start with just like if we consider the visible range imagery and then visible spectrum images, and see what kind of information we can get out of them with the help of computer vision techniques. Just let us quickly recap how deep learning is used for normal images, keeping the remote sensing aspect aside. So, like we know that a normal visible spectrum images, like they are basically stored as 2D or 3D matrices in a computer. So, like it's like they are pixel values. So, it's like let us say that I have an image of size 640 cross 480. So we can see these kinds of things in our machine. So that basically means that there are 640 rows. It's a matrix of 640 rows and 480 columns. And each of these elements is basically a pixel. Each pixel has a value between 0 and 255. And high values of the pixel means it's more brighter, and like low value means it's darker. And additionally, nowadays most images I mean, for all practical purposes, all images are multi-channel. That means like there is normal color images which we see is we know that normal color can, like we know of the color spectrum which we like is decomposed into the R component, the that is red, green, and the blue components. So the images which we see in our computers in a daily life, they are like RGB images. So if we are talking, and they are all 3D images. So if we are talking about like if we denote the image by x, and if I say x of ijk, so since it's 3D, so like we can like have three indices. This means that the we are talking about a pixel on the ith row, the jth column, and the kth channel. So channel in normal circumstances, channel means a color channel. Though in case like we will see in case of remote sensing imagery, it can mean very other different things also. But for normal visible range images, like it just means that these are the color channels. And there are typically three color channels: the R, G, and B. Now, like if you look at this image, it looks it probably like you may be tempted to think that this is something like a very low resolution image of the face of a bearded man or a mustached man. That is, these dark colors indicate their hairs, and these dark colors here indicate their beard, and these black things may indicate their eyes and so on. So it's like if you take the picture of a person's face and then coarsen the image gradually by merging the pixel, it will begin to look like this. And so like if you consider the values of the different pixels, so you can see that the darkest pixels have very low values like 0, 0, 1, 6, 10, 14, etc. And the brightest pixels, like say these birds, which are like which indicate his fair skin. So these are like these have high values like 251, 237, and so on. Okay, so now one important property which images have is that the property of spatial autocorrelation. So spatial autocorrelation is a concept which we have studied earlier in our like while studying the spatiotemporal statistics. So that means that the neighboring pixels are likely to have similar values. Okay, so there are relatively less abrupt changes. There are, of course, because there are edges. Like for example, from here to here there is a change. From here to here there is a change. But usually, like more often than not, neighboring pixels have very similar values. And further, the neighboring pixels are also likely to belong to the same object. So, like say for example, the eyes here, the hair here, like usually an object is not restricted to an isolated pixel, but it usually spans several pixels. So as you can understand, this is a very low resolution image. So like we can actually just count the number of pixels like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 along each row, and similarly maybe another 12 along each column. So it's like a 12 by 12 matrix, 12 cross 12 image. While typically we see the kind of images that we see typically are maybe even be say 4000 cross 3000 or so on. So the more the number of pixels, like the more the resolution of the image, the more visually appealing it will be, and we'll be able to make more sense out of it. The core at as we go, as we make it coarser and coarser, as we every image as we make it coarser and coarser, like we will be losing out on the details and we'll get only that outline. Now in certain situations that's desirable, and in certain other situations it is undesirable. That is, when we are dealing with the visual spectrum images, and we actually want to see the images or see the pictures, and like understand the pictures in the normal way as we do, we will of course want high resolution images because they can preserve the details. But for geoscientific research, we often are more interested in broader properties. That is, we are less interested in the specific details and more interested in say large scale properties. So in that case, we may want to actually blur out these individual variations and actually try to get a bird's eye view or of a bigger picture, as you may call it. In such situations, I will actually prefer a coarser image. Okay, so like it is once you have a high resolution image, it is very easy to make it low resolution by simply taking the means of the pixel values, or maybe if you want by with a process of what is known as max pooling. That is, you take a block of pixel, say 4 pixels, and you see whichever has the highest pixel value, and you simply retain the that highest value. Like you ignore the others. That is, these 4 pixels, you replace them with a single pixel whose value in this case is 182. Similarly, these 4 you replace by a one single pixel whose value in this case is 174, and so on. So that is the max pooling. Similarly, we can use sum pooling or average pooling also, depending on what you want. So, so image just form the basis of this computer vision, which is of course a very well-known application of machine learning. It is a subject which has really boomed over the past decade or so. So, is some of the important problems which which the computer vision community is interested in. I mean, not related to earth sciences or remote sensing or anything, just with normal visual images. Say one of the problems is image recognition. So like basically so the initial problem of image recognition was as follows. You are given a particular image which is focused on one single object, and you just have to say what that object is. Like, is it a car, or is it an aeroplane, or is it a tree, or is it a human face, or what is it? So that is what the original object recognition problem was. But now, of course, the range or the scope of that problem has been much more expanded due to the progress that has happened in deep learning over the past decade. Now, instead of dealing with images that are focused on one object, we actually consider multi-object images. And the task of the image recognition is to recognize all the or which all objects are present in the image. Like in this case, like you can see that there are 3 sheep, one dog, and a lot of green grass. So like this image will be labeled as this 60% sheep image, 30% dog image, and it should ideally be also be include the grass. But I mean, in this example we are seeing that it has erroneously been said considered as 10% cat image also, even though cat is not present in the image. So uh, that is this is just to demonstrate that these algorithms are not yet perfect. They can make mistakes also. So anyway, so image recognition is the first problem. The second problem is that of object detection. So in case of object detection, what happens is you have some classes of objects, and you are trying to identify every occurrence of that class of objects. So face detection is something which we are all familiar with. Most of us have smartphone cameras which have this face detection feature. That is, as soon as you turn on the camera, it will automatically detect where are the human faces visible in the view of the camera, and it will actually put some kind of a circle or a bounding box around those human face. That helps you to focus the camera on them, because it is assumed that when you are taking an image, you will most likely you will be taking images of people, and maybe less that's why we usually do not have, say, car detectors or tree detectors or things like that. But however, it is also possible to build specific detectors for these kinds of objects also. So like as you can see in this case, like a sheep detector and a dog detector has been developed, and The sheep detector identifies the sheep in the image and also provides their exact locations with the help of bounding box. Similarly, the dog detector also detects the dog in the image and locates it with the help of the bounding box. And then there is this problem of instant segmentation. So instant segmentation is like basically like identify which all objects, I mean foreground objects are present in the image and put some kind of a box around them, or basically distinguish them from the other things. So like so now that brings us to another question of what is foreground and what is background. So there are like various models of in image processing and computer vision which try to identify or try to understand which parts of the image can be called as foreground and which can be called as background. So normally, if we look at this image, that we will as human beings, we will treat the grassy field as the background and all these animals as the foreground. And we can see that there are four animals like this. I mean, irrespective of what those animals are, will it's basically there are four separate instances. So what instance segmentation will do is it will try to highlight every single foreground instance of the foreground objects. So this is a foreground object, this is a foreground object, etc. So as you can see, what it has been done is like it has made a list of those pixels which are associated with one particular foreground object, and it has the like that grouping of pixels has been demonstrated with the help of this color. Similarly, these pixels are associated with another foreground object, so like these pixels have been shown in blue to highlight that and so on. And the other is semantic segmentation. So here you actually have a certain set of categories, and you segment the entire image to category wise. That is, you will say that this part of the image, it belongs to category sheep. That is, all these pixels, they belong to category sheep. All these pixels, they belong to category dog. All the remaining pixels, they belong to the category grass. Okay. So here, like this semantic segmentation is different from instance segmentation in the sense that here we are not really considering the individual objects. We are just considering the classes of objects like sheep and dog. Here, but on the other hand, here the focus is on individual objects which are foreground. We are not focusing on whether they are sheep or dog or horse or cat or what. We are just saying this is a foreground object. I am highlighting it and so on. So these are some of the questions or some of the core problems of computer vision, which computer vision researchers have been trying to address since say 2006, 2007 and so on. So for this purpose, what they needed is a representation of images. So of course an image so if we have to if we have to solve this kind of a problem with the help of computer with the help of some machine learning kind of thing, so the machine learning algorithm will also obviously need some kind of a feature vector which contains the description of the image. So the image is like, of course, like this is a raw image. As we know, it can be seen as a like a large matrix which contains all the pixel values and so on. But that is unlikely to be enough or very, it's unlikely to be a very useful piece of information because it contains a lot of other things also. And we have no idea. I mean, if you just provide this matrix to the machine learning algorithm, it will have absolutely no idea about which parts of the matrix to focus on and so on. And like especially if you look at, say for example, if it look at this pixel, it will find that it's a white pixel. But a white pixel can belong to a sheep, but it can easily belong to many other things also. Similarly, here we have a black pixel. So it will like whether that this black pixel belongs to a sheep or to a dog or what, it will not have any idea of. So it is the raw image, which is basically the collection of the pixels, is unlikely to be very useful for any machine learning algorithm. what is necessary is therefore is to understand more finer aspects of this image, the things, say for example, with which we as human beings we like understand the image. Say like one of the one thing which we as human beings may try to interpret the image is like in terms of like shapes of the different objects. So first of all, where are the or what are the I mean where are the different objects present in the image, what are their boundaries, what are their shapes. So to so that and then or what is like then once we have identified the shape, we may be interested in say the color, the texture, and or the various other sub parts of that object and so on. So how to like get these kinds of information, how to, from the raw image, how can we get the shapes of the different objects, or further how can we represent the textures of the like the different objects and so on, right? So for that, what is needed is a very rich representation of the image, not only the whole image, but also parts of the image. Because like as you can see, it's not that the whole image belongs to the category sheep, but there are sheeps present in the image, but only in specific parts. Now, whether it is that part or this part or this part, who will know? Right? So what is necessary is we build very rich representations of not only of the entire image, but also of various parts of the image at various scales. That is, at the top of the scale we have the entire image. At the next level we can actually have, we may have half of the image, and one half of the image and another half of the image. Further, at further image, I mean, at further level, we may be focusing on like various quarters of the image and so on and so forth. So basically, what we need like a very rich representation of both the image as a whole and as parts. Now, this representation can be done either using the raw pixel values as is being done here, but as I said earlier, that's not very useful. So what people or the traditional image processing community have traditionally done is to use filter outputs. That is, there are certain mathematical functions which can be applied on these images, and what they will do is at different locations of the image, they will calculate certain things, or like they will take the pixel values or surrounding pixel values as input and give some output. Now, different filters or different filter outputs give us different kinds of information. So we'll not go into the details of all those kinds of things. That is for image processing people to study. Nowadays, what people do, I mean, there was a time, say around 2005, 6, 7, 8, when the computer scientists spent a lot of energy trying to understand what can be good features for the image. Like for example, here as you can see, here is an image of a leaf. Okay, this is a raw image. So now what people have done is like they have applied various feature or filters on this image, and as after that the image looks like all these things. Like so there are five different filters. Each of these filter, when you run it on the image, it will act on different parts of the image and it will get a response. That is, the output of the function is called the response at that particular point. So as you can see that these are the responses of the different filters at different parts of the image. And so like you can, as you can understand that in some of these like seem to be highlighting the texture of the thing, some may be high focusing on the edges. Like in this image you can see the edges corresponding to these veins in the leaf, those edges are very pronounced. So there are these edge detectors on an image which actually I try to identify those places where there are sharp change in pixel values, and those places are known as the edges. So the edge detectors, what they do is they highlight those edges in an image, and helps us to like in a sense that helps us to give an get an outline of the image. And similarly, there are some other other filters which try to identify various corner points, that this is one particular corner point, so at this point it will have a high response. This is another corner point, so at this it will have another high response. These are not corner points, so it will have low response, etc. So there is a like a wide array of such features like these, which are not necessarily very well understood, but like that is, if you like apply lots of those, or if you calculate lots of those features from any image and create a very large feature vector and provide it as an input to a machine learning algorithm, it will probably give you some kind of result. Okay, but it gave like that way some progress was made till say around 2010, 11, 12, but it was not a very impressive progress. After that, what people started to do is to, when once the deep learning happened, or once the deep learning, the power of deep learning became known to everyone, then people started just forgetting about these kind of handcrafted image features, and instead they started using the deep features. So what is a deep feature? So deep feature is that you just take the images, the input images as is, and you provide them as inputs to various neural networks. So the neural network, of course, has different layers. So that at the different layers, it will produce some kind of results. And those results are, of course, to be passed on to the subsequent layers and so on, as the way that has been, that is in the, according to the scheme that you can see here. So this is the famous AlexNet. So these blue, brown, orange, these are like various layers of the neural network. At each layer, like we can, some kind of mathematical operations take place, which I guess most of you know. And the now as a once those mathematical operations are done on the input image, so we can say that we get another image which is a transformed form of the initial image, and then that transformed image is again proceeds to the next layer for further processing, and we get another transformed image, and like this. So subsequent, like step by step, the image is transformed into many forms. Ultimately we reach a fully connected layer in which like all the things are just stacked together. I mean, the responses from all the different pixels are stacked together to form a very long vector. And after that, it is like we get some kind of a concatenated feature, which is passed as a classifier, right? So the maps of the I mean that is the representations of the image which we get in the various intermediate layers of the neural network, they are often known as the feature maps. And these feature maps, they basically they form the basis of like these what is known as deep features. So unlike this approach where we actually developed some kind of filters to identify the edges of the image or the corners of the image, or say the texture of the image and so on. In this case, we are not really, in case of deep learning, we are not really building the feature maps with any specific purpose. It's like there is one layer of neural network which responds to the to the input image and produces its produces the response image. And like we do not really try to infer whether that response image, what exactly is the meaning of it, or even if it has any meaning or not, and so on. But we just use whatever response it is giving, we just collect and we treat it as a deep feature. Of course, there has been a lot of efforts at interpreting the results of these deep features. That is, people actually look into the feature maps produced by each layer of a neural network and try to understand what that feature actually may mean. and people also try to draw some parallels between the deep features and the handcrafted features which were used earlier. That is, people sometimes say that if you use this kind of a neural network, then it's for the first layer will identify the corner points. The next layer will identify the edges. The third layer will identify the texture, and people say things like that. Of course, these are open to interpretation. So, but basically, if you see so convolutional neural network is a kind of neural network that is very well known in case of like image processing. So the I even before this even before we came to the concept of deep learning or neural networks, the convolution has always been an important has been a part and parcel of image processing. And even when we were dealing with handcrafted filters, the operation of convolution was used. So what is convolution? Convolution is basically something like this. It is like you have a filter like this which respond which has us it's a usually a like a two-dimensional matrix. So its size may be 3 cross 3 or 4 cross 4 or something like that, but it basically it represents some kind of a pattern. I mean, as like a small pattern. So if you see so this kind of a filter is sometimes also known as a kernel. So if you look at this one, it's like saying that the central element is 8, all the surrounding elements are -1. That basically means that it is looking for such a situation where there is an isolated point whose pixel value is high at the surrounding places the pixel values are low. Okay, so that kind of structure so basically we are looking for something like say some corner points or something like that, where we see where this kind of a structure may be found. So that now what we will do is that this is the image where these small squares, these are the pixels. What we will do is we will slide this filter across the image row by row and column by column. And so right now this is the this is where the pixel, I mean the filter has been placed. So since the filter is 3 cross 3, so it occupies or it covers a 3 cross 3 sub image. So there what we do is the operation of convolution, namely the pixel value at every pixel, each of the pixel values is multiplied by the corresponding filters value. So this pixel value is going to be multiplied by this. This pixel value is going to be multiplied by this. This pixel value is going to be multiplied by this, and so on. So this way we get 9 products, and we add up those products and place them in the pixel which is at the center. So this is where the filter is sitting now. So I put it, that value which I got, I put it here. Next, I slide the filter from here to maybe covering these 9 things, these 9 pixels. So again, we repeat the operation. So now this pixel value is multiplied with this pixel value is multiplied by this, and this pixel value is multiplied by this. Similarly, this pixel value is multiplied by this, and this pixel value is multiplied by this. So the 9 products we again get, and we put it in the center. Now, right now, we are covering these 9 pixels. So this is the center. So here the value is put here. And this way, we just pass on the this filter across, slide it across the entire image. Row one row, we slide it row wise, and we also slide it column wise. Okay, and this way at each of the pixels we get some response. Those responses are these pixels are stored in I mean these pixel values are stored here in the middle. Okay, so this way we get an output image. So if this is the input image and this is the convolutional kernel, then this is the feature corresponding feature map that we get. So what is the, so like you can see that in the feature map, what it shows is basically the response of the convolutional kernel at different places. Fine. So now this operation which we mentioned is this is called the convolution operation, which involves multiplying like that is there is some set of weights which are to be multiplied by input values, and then those products are to be added up. Fine. Now this operation is like analogous to the kind of operation which is done in case of a neural network, right? So like now there like we can actually build a neural network which replicates this kind of a convolutional operation. So let us so that such a neural network is known as a convolutional neural network, or rather a layer in which this kind of a convolution operation happens is called a convolutional layer. So let us try to see what exactly that means. So let us say that we have an input vector like this and a weight matrix like this. So those of you know neural networks will understand that like at every layer of the neural network, basically we have a like if you consider this as a fully connected neural network, right? Then in that case so these what we are seeing is basically something like an edge weight. That is, there is a the input is 6-dimensional, the output is 4-dimensional, and from every input to node to every output node, there is a link, and those the weightage of those links are indicated by these values. Correct? So then what is to be done is like you basically do an operation which is analogous to, which is basically matrix multiplication. So you can do the matrix multiplication, and like that is this weight matrix you will multiply with the input vector and you will get the output vector. So as you can see, like that is what is happening. So you do 4 into 1 which is 4, 2 into 2 which is 8, 4, so you add up 8 minus 3, that is 5, and these are all 0. So you get the value 5, you put it in this node. Next comes these weights which connect the input to the second node. So you again do the operations and you can convince yourself that the value is 0, which you place it here, and so on. Okay. So this way when you do the matrix multiplication in the standard neural network, this is the output vector which you get. Now, if you look at in details at these weight metrics of the neural network, this is what it looks like. So you'll see 1, 2, 3. Okay, and then 0, 0, 0. This is what the first column of weights looks like. If you look at the second column of weights, it's like the same things, the same values, but the 1, 2, 3 has moved down a little bit. Then again, in the third row, it has moved down further, and so on. So you can see that there is a single repeating structure 1, 2, 3, which is moving in all the rows. Okay. Now the magic is that you can actually see that if you do the convolution operation of this repeating structure 1, 2, 3 on this input vector, what you will get is just this output vector itself. So what does it mean? So like earlier, so here I was telling you what is meant by the convolution operation, that is you slide the filter over the matrix, you slide it row wise and column wise. Now, of course, we have the vector, so there is no question of sliding it column wise. We have to slide it row wise only. So initially, this filter 1, 2, 3, it will cover these 3, then it will cover these 3, then it will cover these 3, and finally it will cover these 3. So when 1, 2, 3 is covering these 3, you will again do that mathematical operation and you will get the value of 5, which you place here. Then this 1, 2, 3 will like you will have placed, like you will slide it down and cover these 3, and you will get the value of 0, which you will place here, and so on. Right. So you can see that like basically these two operations are equivalent. They will give the same result. Either you can take this kind of a structure or this kind of a filter and convolve it over your input vector, which will give you this output. Or you can consider a fully connected neural network with these edge weights, which will also give you the same output. Okay, so the this is a case of this is a situation where a neural network is replicating the or is emulating the process called convolution. Okay, so like if this kind of a thing is done in any layer of a neural network, that is called a convolutional layer. So along with convolution, there hand in hand goes another operation called pooling, which I also mentioned earlier. So that is like you have an image or a matrix like this. You just divide it into different blocks of a size and a stride. Size means the every like you will deal with size block size 2 means you will deal with 2 cross 2 image of sub images like this 2 cross 2, this 2 cross 2, this 2 cross 2 and so on. And stride means like you will be hopping like so suppose this 2 cross 2 image you will start with. After that will you consider this overlapping block or will you consider this non-overlapping block? So that depends on what your stride is. Stride 1 means you are initially focusing your filter on these 4 images. Stride 1 means after once you have finished this operation, then you will slide it by one step and focus on these pixels. So that will of course involve some overlapping. Alternatively, from these two, you can slide it by 2 steps and come here, and then these 2 cross 2 you will be focusing and so on. Okay. So now when you are focusing on these two, so suppose you have focused on a block size of 2 and a stride of 2. So you focus on these 4 pixels, their largest value is 6, so you put it 6 here. Then you move it to by slide it by 2 steps. You now focus on these two. So here the maximum value is 8, so you save as 8. Similarly, here in this block, again vertically you stride it by 2. Now we are focusing on these two things. So here you will see that the maximum value is 3 and here the maximum value is 4. So this large 4 cross 4 image, he has shortened it to a 2 cross 2 image. Okay, and whose pixel values are like this. So you can see that you have only preserved the higher values of the pixels and discarded the lower values, or only the brightest pixels are preserved. Okay, so similarly, you could have also used a different block size and a different stride. In that case, you would have got a different result. Okay, so these convolution and pooling, these are the most fundamental operations of a neural network that deals with images. And that way we get what is known as a convolutional layer. So usually a standard convolutional neural network follows like this. So we have the input layer, which is basically the full image itself, like flattened as a single vector and provided. And then or it can be I mean it need not be flattened, it can be provided as a full tensor or the full matrix also. Then what happens is we have a convolutional layer where basically the convolution operation happens. Like we have already seen how the convolution operation can be implemented using a neural network. So here the convolution takes place and after followed by one layer of pooling. That is so. So obviously when we are when we are doing pooling, or the convolution, the size of the image is going to change. As you can see, in case of pooling especially, the from a 4 cross 4 image became a 2 cross 2 image. Similarly, a convolution can also cause the image to shorten. So this way we gradually pass the image through a number of layers, and at each of those layers basically the image also becomes smaller and smaller, but the pixels themselves, they become more informative. That is, you are basically doing things like in case of pooling, you are throwing away the useless pixels or the unresponsive pixels and preserving only the responsive pixels. And in the convolutional layer, you are basically merging the different pixel values. and you are that is instead of treating each pixel separately, you are interacting every pixel with its neighboring pixels, and so on. So this way, you basically pass the input image through a stage of convolution and pooling, and finally you get a representation which is provided as a fully connected layer. And then basically your image is reduced to a very large vector, and that large vector is provided to on the basis of that you do your classification. So you can use something like a softmax function and get the probabilities of the different classes if you are looking to solve a classification problem. Or you can using that fully connected layer, you can do something else. You can create another image also, and like that's called an image to image translation. So that's a different issue. So but basically this is the idea of a convolutional neural network. Okay. And and each layer of the convolutional neural network, say the convolutional layer and so on, like you can see, will it will produce its response. So this was the input image. Then after one round of convolution, this is what the response image will look like, may look like. Say like as you can see that that some parts of the image have been blurred out and some other parts have been preserved. Then after another round of convolution, the image may look like this. Again, this information may, as it suggests, is like focusing more on the outlines, blurring away all the internal details. In this case, it shows something else. This one may be focusing on some kind of a color map and so on. So each of these layers or the feature maps, they provide some new representations of the image, and the neural network basically takes or as inputs all these different representations, and based on it, it does the classification. Now, these representations, whether they can be physically or visually interpreted or not, is a different question. But at least as far as classic machine learning is concerned, it is found that these representations are very successful. In fact, they are more successful than the earlier representations, in which we had tried to say locate the corner points or the edges or things like that with some so-called handcrafted features. So that is basically the story of convolution and convolutional neural network. So like when you provide an image as an input to the convolutional neural network, what it will do is it can do some kind of a classification like this. It will take the input image, it will pass it through so many layers, and then like in the output layer, if it is a classification problem, there will be one output node for each of the possible classes, and then those nodes will basically store some values which will indicate the probability of the image belonging to that class. Okay, so as you can see in this case, it is saying that corresponding to the zebra, the output is 0.7, which indicates that this is probably a zebra. But the important thing to note is that, as you can see, it is not focusing on the entire image at a time. It's like parts of it, maybe these few input images, I mean input pixels, are uh, represented by this single pixel here. Maybe another set of pixels here will be represented by another pixel here, and so on. Similarly, again, in this image, this image, it will have its own set of pixels. So again, one set of pixels, like this set of pixels, will be represented by a single pixel in the third layer, and so on and so forth. Okay, so it's like what these things are doing, what these filters are doing is that each filter is focusing on only a part of the image and trying to build a representation of it. So this is the general idea of how the convolutional neural network works. And then this kind of thing is often used for object detection. So there is this framework called YOLO. YOLO stands for you only look once. So the whole idea is that you have an image like this, and in that image you have to look for certain kinds of objects. So let us say that as you can see, this image has three important objects, three foreground objects, if you say, the dog, the cycle, and the car. So what this image what the task is that it will try, let us say that we already have trained dog detectors, cycle detectors, and car detectors. So what it will do is it will try to look for dog, cycle, and car in this image. So now the dog can occur anywhere in the image and at any scale. It's possible that there is a small dog can be accommodated in a single pixel. It might be that the whole image is focusing on a dog only. Similarly, this car, it covers only a small, only 3 pixels, but in general, a car is a big thing and it can cover, span multiple pixels also. So when we are searching for a particular kind of object, we have to search at multiple scales and at multiple locations. So generally, that's a very difficult task, but it is but what this YOLO or you only look once feature does is that it builds this kind of a very rich representation of the image, where it considers boxes of various sizes or bounding boxes of various sizes, and in each box it tries to classify as one of the different classes under that it is interested in. Like it will take a one box like this, and say a box which is focusing on this region, and try to classify it like, do you think this box belongs to a cycle, or do you think it belongs to a dog, or something like that. It will try to attach probability scores to of all the classes to each of those boxes. Okay, and that is, this kind of an operation is possible because of the structure of convolution. That is, as I said here, like we are focusing on different parts of the image, and uh, uh, like uh, and then doing the processing for those parts. And then at subsequent layers, what we will do is we will also consider the interactions between different parts of the image. Furthermore, the different parts of the image that we are talking about are actually can be overlapping. They can be of multiple sizes. So that's the like that way we are actually able to through a series of operations, we are able to attach some scores to each of the different boxes of the image, and then again combine all those scores. So once we have got the scores of all the all the image, all the different boxes in the image, then those scores are combined through this kind of a box prediction layer, which finally gives you the things like what you are looking for. It's like at this stage you have found, what has been found is that these pixels, they have a high probability of being belonging to dog class. These pixels may have some high probability of belonging to, let us say, the bicycle class. These pixels may have high probability of belonging to the grass class, and so on. So based on that, it will do some kind of an image segmentation. I mean, based on these pixel probabilities, it will identify some kind of a bounding box where the probability of a particular class is the highest. Okay, so this is the how we do the image I mean object detection. And related is the task of semantic segmentation of images. So semantic segmentation of image basically means that you have a full image, you segment it in such a way that or you coarsen the image in such a way that all the pixels below, which lie inside one object, they have the same pixel value, but the pixels in different objects, from different objects, they have different pixel values. Like for example, you have this input image, so you can see cars, you can see road, you can see lamp posts, you can see building, you can see tree, etc. So this is the input image, and in the output image you can see all the road pixels have the same pixel value, all the car pixels have the same pixel value, all the house pixels have the same pixel value, tree pixels have sky pixels have another value, and so on. So this is also achieved by the process of convolutional neural network. So basically what as I mentioned earlier also, in case of the convolution and pooling layers, what they do is they basically coarsen the image. Like the convolution layer, it causes every pixel to interact with the surrounding pixels, and the pooling layer basically it stores the pixels with high values and throws away the pixels with low values. Okay, so as a result, like if you do this progressively, you will get an increasingly blurred image. And then once you have a blurred and a smaller image, so as you can see, the image size progressively gets smaller and smaller as you go. And then once you have got a small blurred image, from that you have to upsample it to produce the output. So the input and the output will have to be the same size. Okay, so that we can get a pixel to pixel mapping. So that is done by this kind of a structure, which is known as sometimes called an U-net, where the like the input images are provided, the input images are progressively downsampled and made coarser and coarser, smaller and smaller, until it reaches like a what is sometimes known as a bottleneck layer. And then from that point onwards, it is again upsampled to make a like a to restore it back to its original size. But the thing is, when you have reached this layer, that is, you have already thrown away a large part of the information. That is, at every pooling step, you are throwing away all the pixels with the low value. So you are keeping only some pixel values. So once you have reached this, you have like your image already has lost a lot of information, and you can argue that it has lost the detailed information and preserved only the significant information. Now from that you have to like recreate the image, which is what is done in case of image segmentation. So as you can see in this case, so these are some medical images. So this is might be the image of the human brain, and you can see that one part of it has like it has become basically a binary image, which is like showing one part, highlighting one part of the image in white, the rest of the image in black, and so on and so forth. Okay? So this is the task of image segmentation. So both of these problems of object detection and image segmentation are very important in the task of remote sensing or satellite imagery, especially those in the visual spectrum. So we will discuss more about this in tomorrow's class. Okay. So that brings us to the end of today's class, and I would like to remind you once again that all of you must provide the topics of your seminar